Hi everyone. So let's today talk about abstract algebra. So abstract algebra very important in modern mathematics as well as physics also for studying especially the structure and symmetry. These two things is very crucial to understanding or reason that we are studying the abstract algebra. So let's discuss about some basic definition we are using today's lecture. Like what is the binary operation or binary composition? Like if we start that function, then we need to function and their properties. Similarly, if we want to study the group, then there is a function or a special kind of function whose name is called binary operation. So let's talk about that what is the definition of binary operation or binary composition. Let G be a non-empty set, then any mapping or function from G cross G to G itself means their ordered pair and their codomain both comes from the same set G, then it is called binary operation or binary composition. It means that their ordered pair have a specific function or a specific function has to define with this ordered pair, and codomain is also comes from that same elements, same set G, then it is called binary operation on a set G. A star B equal to C, and this C is also comes from G, then ABC belongs to G, then it is called binary operation. Associative binary operation. Associative binary operation happened with the three number or three elements with that same set. So binary operation star is called associative if A star B star C equal to A star B, means if you apply the bracketing in different place but the result cannot be changed, then that property is called associative property. Commutative binary operation. A binary operation star is said to be commutative if A star B equal to B star A, means if you change the order with the same binary operation there is no change in your answer, then it is called commutative property. And this is the formula important for CSIR net or GATE examination. Like if you have if you have n elements in particularly set G, then total number of commutative binary operation is n to the power n into n plus 1 by 2, and total number of non-commutative binary operation is n to the power n square minus n into n n to the power n into n plus 1 by 2. If we talk about the total number of operation, then you may say that G cross G, total number of function. If you talk about like G to H, then if you have G have a m element and H have n element, then total number of function is n to the power m. Similarly, because here G cross G to G, so here G have element n and it is also n to n, so total number of function is n to the power n into n, then n square. So if you subtract total function, total number of non-commutative binary of total function from n to the power n square minus total number of commutative binary operation, then you get non-commutative binary operation. Okay, existence of identity. Sometimes it's happened that you do not have a identity element, or it may be possible sometime if you sometime identity element mainly depends on binary operation. So if let G be a non-empty set and star be the binary operation, and E, let us assume that E be a identity element, and make sure that that identity element comes from the same set E, such that A star E equal to A star A equal to A for all A belongs to J, then E is called identity element or neutral element, because in this operation you can see that A star E equal to E star A, that same element comes, so that identity element doesn't involve, actually involved, but there is no impact on the final result. That's why it is called neutral element with respect to star. So mainly identity element depend on binary operation, and existence of inverse element is actually depends on identity element. Okay, and here it is using a word existence, so there is just some possibility where under that binary operation there is no inverse element exist for the each element. That's why here we use existence of inverse element. Let G be an empty set and star be a binary operation, E be the identity element, then A dash belongs to G or A prime belongs to G is said to be inverse of A, or and vice versa means the this element have inverse of this. It means that this element is also inverse of that element, such that A star A prime equal to A star A equal to, if we get I, then we say that A have inverse element of A dash and A dash have inverse element as A. Next, we will discuss about algebraic structure. A non-empty set G occupied with the one or more binary operation is called algebraic structure or a star algebraic structure. It means that there is a one binary operation, it may be involved, two in binary operation may be involved, or multiple binary operation may be involved to constructing a structure. So such type of structure is called algebraic structure. Actually, I already told you from starting that mainly algebra is studying because of we want to study the structure as well as symmetricity. So you may think that if you have a same domain, but if you change the configuration, then you produce a different element. Like we all are made of carbon, we all are made of carbon, but if you change the structure, then you get graphite, diamond, and some other species, because in each and every entities or living entities have carbon, or some non-living entities also. So in the same fashion, you can relate that algebraic structure, then you can have a better understanding or better grasp that what is algebraic structure and why this structure is important for study the group theory as well as ring, field, integral domain, and this all things comes from this structure. You may take the two binary operation, three binary operation, here be taken as a star, and zero, a smallest zero is as a algebraic structure. So let's proceed on step by step. How can we define a group? So what is group wide? A non-empty set G is said to be group wide with unique binary operation. Sometimes binary operation is also referred as a closure property. So if a set certain binary under certain binary operation, if satisfy, then it is called group wide. So natural number with respect to plus, integers with respect to positive, complex number with respect to positive, rational number with respect to multiplication, integers with respect to subtraction, these all form a group wide. Like if you take the two number -3 -5, then we get -7, and -7 is also comes from Z. Then we can say that this hold closure property or binary operation, then it is called group wide, and you can simply verify these other examples also. What is semigroup? An algebraic structure if satisfy the associative property, then it is called semigroup. Means for having a semigroup, you need to check two things: closure property, A star B belongs to G for all AB belongs to G, and and associative property. If two properties satisfy, then it is called semigroup. Third one is monoid. A semigroup G star is said to be monoid if it has an identity element Like if we want to say monoid some structure, then you have to verify that whether this uh, set under that binary operation satisfy closure property, associative property, as well as identity property, then it is called monoid. And fourth property is called group, that are interesting for today. Let G be a non-empty set and star be a binary operation. Then the algebraic structure G star is a group if star is a binary operation satisfy the following property. First property, closure property, or you may say that the binary composition or binary operation may satisfy. Second property, associative property, A star B star C, means that associative property allow you to use bracket anywhere and then calculate your answer, then there doesn't defect of your final answer. Existence of identity element A star A equal to A star E equal to A for all A belongs to G, and existence of inverse if possesses if each element of G, means there is every element of G if exists their inverse element under that binary operation, then we can say that A have inverse as A inverse, and A inverse have inverse element as A, or vice versa. Okay, and for the abelian group, that's the fifth property is must hold. Then it is called A star B equal to B star A for all AB belongs to G. Then it is called abelian group or commutative property. Okay, so these are the example that is more interesting that we should consider and we can solve. So I request you, every viewer, that you should solve this all question and check whether that function is group wide, this structure is group wide or not, monoid or not, semi group or not, like that. So here I can take an example like n plus. If you take n plus, then if you take two number 2 plus 3 belongs to 5, 5 and 5, 5 also belongs to natural number, then closure property satisfy, it means that it is a group wide, semi group, monoid, as well as group abelian group, you can see in this way. So I randomly just check and just you should follow it also. So if you take two natural number, add them, then you can easily get uh, another natural number, then it is a group wide semi group. If you take a three natural number and add them in any order, then there is doesn't effect of your answer, then it is called semi group. And monoid, it's need a with respect to addition, we need with respect to addition 0 is identity element, but 2 plus 0 equal to 0, but actually 2, but 2 0 does not belongs to natural number, so in this case we cannot say that this structure is monoid. So there is no monoid, so we cannot, there is no need to check that group wide or abelian group. Similarly, you can check that natural number with respect to multiplication. With respect to multiplication, you can multiply two natural number, you get once again a natural number, so that one is a group wide. If you take three natural number, multiply in any order, then you again get a same answer, that one is called semi group. Monoid, if you talk about, then 1 is identity element, 1 into 7 equal to 7, so 1 is treated as a here as a identity element and 1 belongs to natural number, so it satisfies the monoid property, means existence of identity, then it is called monoid. And if you talk about that group, but 7 have inverse 1 by 7, then you can get 1 as a identity element, but actually 1 by 7 is not a natural number, does not a natural number, so in this case this is not a group, and we cannot no need to check about abelian group. Similarly, if you take the natural number and operation is multiplication, so 2 minus 3 equal to minus 1, minus 1 does not is a natural number, so we cannot say that one is a group wide. It does not hold the closure property, so no need to check other thing, so it's failed to be. Similarly, you can check that for z plus, z minus, z plus, and q plus, q minus, and q dot, and something like that. Q star is actually all those uh, positive rational number, all negative rational number, all positive rational number. Here it is all positive rational number. And let's talk about in this example m and r. So matrix with real entries of n by n order. So how can we check this matrix form a abelian group or not? So let's check in this way. If you have let's do with this simple example 2 3 5 7. If you add two matrix in similar fashion, uh, then 2 plus component wise additions, and 2 plus 3 equal to 5, 7 plus 3, 7 plus 3 equal to 10, 5 plus 7 12, and 7 plus 6 13. So this is once again a matrix, so this follow the closure property. Second, matrix चूंकि this operation is component wise addition, so uh, uh, this is also hold associative property. Third one is identity element, so you can take a 0 0 a b c d, and with operation 0 0 0 0 you can get a same matrix A B C D. So 0 0 is treated as a identity element, so this have a identity element as well as for inverse, because here it is a real entries. Then in this case minus a b c d, this have a additive inverse minus a minus b minus c minus d, so this hold zero matrix. So in this way we can say that this form a group as well as abelian group also, because if you change the two matrix in any order, then there is doesn't effect with respect to addition, so this form a group. If you talk about in the matrix multiplication, then two matrix if you multiply, then you once uh, again get a ma matrix. So closure property hold, associative is inbuilt hold. You may have studied in your linear algebra course or matrix course. So associative, if we talk about identity, then 1 0 0 1 is their identity element. You can multiply with any number, does not affect their answer A B A C. So this is identity element, but every matrix need not to be a inverse, because its first restriction is that if matrix must be non-singular, then their inverse exists. So there is a chance that some real number with n by n order matrix have determinant in 0, so their inverse does not exist. So this forms group wide, monowide, as well as semi group, but uh, cannot form a group because of that. Uh, for this, you may make a table that you can better understanding of this group. Like there is operation is multiplication 1 minus 1 I minus I 1 minus 1 I minus I 1 1 into minus 1 1 into I minus 1 into 1 minus 1 into minus 1 1 minus 1 into I minus 1 into minus I plus I. I into 1, I into minus 1, minus I into I, minus 1, I into I minus 1, and minus plus 1. Once again minus 1, I into 1, minus I into minus 1, plus I, minus I into I, plus 1, and minus I into minus I, minus 1, minus minus plus, and I into I equal to minus 1. You can see in each row or each column there is all those four elements is available there. So in this way, if all those four elements is available there and there is no other external element is there, then in this way we can say that this four element form group under multiplication. And by this table or Cali table we can see one here, one is as a identity element, and I have inverse with minus I have inverse with minus minus I have inverse is my I. So in this way we can easily check uh, that whether function is identity or not. Similarly, you can see that multiplication 1 omega omega square, 1 omega omega square, 1 into 1 1 1 into omega omega 1 into omega omega square, and actually this is the cube root of unity, so omega q equal to 1. So omega into 1 omega omega square, omega into omega omega square, omega into omega cube, value 1. Omega into 1 omega omega into omega omega square, omega into omega square, omega square, omega square into omega square, omega square, omega square into omega omega cube, value 1, and omega square into omega square, omega 4, and omega 4 omega cube equal to 1. So one remaining 1 omega is there. So you can see that each row, or you may say each column, all those three elements is available there. So this form is also group, means cube root of unity also form a group, even abelian group also. This one is also abelian group, this one is also abelian group. Okay, and similarly you can see that the nth root of unity, and this is for you, you can use in this way, like I would like to just give you some reference that you can easily do it. X to the power n equal to 1, and 1 is written as like cos 0 plus I sin 0. If you generalize this value, then you may add cos 0 plus 2n pi, or you may add 2r pi plus I sin 2r pi, and this thing is also written as the cos 2r pi plus I sin 2r pi, and e to the power I 2r pi, and sorry, no need to written that. And if you take this thing like power 1 by r, x equal to, then cos 2r pi plus I sin 2r pi per power 1 by n. And by de Moivre's theorem you can say that cos 2r pi by n plus I sin 2r pi by n. If you change the value of n, then because this one is also periodic function, this one is also periodic function, so this all elements comes under a circular region, because their radius is 1. So this form is also nth root of unity also form a group. And addition group of modulo n, you can see this Cali table also, that if there is a addition modulo 5 is written there, then you have to write out 0 1 2 3 4 with respect to addition. If multiplication modulo, if there is a multiplication modulo 7 is written there, then you have to write down the elements as a 0 1 2 3 4 5 6, and there is addition modulo 8, then 0 1 2 3 so on 7 3 4 5 6, something like that. And how can you calculate that? Here it is, here we are interested in modulo, or you may say that remainder. Like addition 0 to 4 is written there, 0 plus 0 1, 0 0 1 2 3 4, there is no problem. 1 plus 0 1, 1 plus 1 2, 1 plus 2 3, 1 plus 3 plus 1 plus 4, 1 plus 4 5, because this is addition modulo 5. So 5 divided by 5, we get remainder as a 0, so we can write down here 0 as a remainder. 2 3, 2 plus 1 3, 2 plus 2 4, 2 plus 3 5, divided by 5, remainder 0. 2 plus 4 6, divided by 5, remainder 1, then it is written down here 1. 3 0 3 plus 1 4, 3 plus 2 5, remainder 0. 3 plus 3 6, remainder 1. 3 plus 4 7, remainder 2, so write it down here. And similarly in the 4, you can see in each row or each column there is a every element is written there, 0 1 2 3 4 5. So in this way we can say that addition modulo 5 is form abelian group, because you can see here 4 plus 3 equal to 2, and 3 plus 4 equal to 2. So we can easily say that this one is also form a group. Okay, and here it is written down some multiplication uh, multiplication group of integer modulo n, g equal to 1 2 3 4 to n minus 1. If there is a multiplication modulo is written there, then you have to write down start from 1 to just one number before. Like here it is a multiplication modulo 3, then you can see 1 2 3. Oh my god, I write it down is wrong. We have to write down only 0 1 2. Okay, in 3, 1 into 1 1, 1 into 2 2, 2 into 1 2, 2 into 2 4. Since it is a multiplication modulo, 2 into 2 4, divided by 3, value 1. So in this way this is called group, because it has only two elements, so this form also a group. Sorry, this is written wrong. And in multiplication modulo 5, so here you can see 1 2 3 4, and the same operation, 1 into 1 1, 1 into 2 2, 1 into 3 3, 1 into 4 4. So one is here treat as a identity element, 2 into 1 2, 2 into 2 4, 2 into 3 6, multiplication modulo 5 5, divided by 6 divided by 5, then remainder is 1. 2 4, 2 4 are 8, multiplication modulo 5 divided by 5, remainder is 3. 3 into 3 1, 3 into 6, modulo 5 divided by 5, remainder is 1. 5, 3 3 are 9, divided by 5, remainder is 4. 3 4 are 12, 12 divided by 5, remainder is 2. 4 into 1 4, 4 into 2 8, remainder 3. 4 into 3 12, remainder is 2. 4 into 4 16, remainder is 1. You can see in each row or each column every element is written there. Then in this way we can say that multiplication modulo 5 form a group. Here is some special group like general linear group of degree n. It is also written as GLNR, means group of linear group of order n, and their interest comes from real number. So set of all n by n non-singular matrix means the determinant must be not equal to 0, with real entries denoted by general linear group of n with real entries form a non-abelian group. So means GLNR always form non-abelian group because it does not hold commutative property. A B C D E F G H not equal to E F G H A B C D. That's why it is not a non-abelian group. But rest of them is also satisfied because here all determinant is not equal to 0. It means that their inverse must exist, and that's why they form non-abelian group. Under matrix multiplication, this is called the general linear group of degree n. And the second is, you may say, the subset of G special linear group, set of all n by n non-singular matrix whose determinant is equal to 1. Here it is the specific case. In this way their determinants must be 1 with the real entries denoted by special linear group of real entries form a non-abelian group under the matrix multiplication, and this is known as special linear group of degree n. And in this case you can see that G L N R and SLNR, uh, the relation between both of them, this one is subset of this because there is a specific case is written there. Okay, and this four example is also most important. There is lots of question asked in CSIR net examination like permutation group. Let's take a three number. Number A equal to 1 2 3, and their permutation total power set 5 1 2 1 2 1 3 2 3 1 2 3. These all possible power subset. And if you take the intersection, if you take the intersection of 1 and 2, and we take intersection, so both intersection have 5. So in this way we cannot say phi, and phi comes from this element. So phi comes from Pn or Pa, then it is called closure property satisfied, then there is no problem at all. Okay, associative property, if you take the intersection of three number, then you may also get always empty set phi, like 1 1 2 1 3. So if you take that, here it is a 1 is there, and you can say that if you take this one first and then with this, then also 1 is common among them. The associative property hold. If we talk about identity property, so this one is crucial. Identity property, like E is a set of identity element intersection with some element 1 2, then must get 1 2, but actually we get 5. Both intersection have 5, but actually we are interested in 1 2, so there is no identity element, not identity element, so this does not form group. Means that this form group wide, this form semi group, this, but this not form monoid. Monoid fail as well as group is also fail. If you talk about then their union, so if you talk about then union, then I think so you may check here also once again. Okay, so we need to check under that union operation. Okay, so by the help of union operation, you can see that 1 2 union 1 3, you can see that 1 2 3 also comes from PA, so there is no problem. Closure property satisfy, associative is also satisfy. If you talk about identity, then 1 2 union 5, then because this is union, so 1 2 is there, so identity element exists, but there is a no inverse element is there who's provide you identity element. Like if you take the 1 2 once again and their inverse element, inverse set equal to 5, then there is no such inverse set is available there, then it is called, then we cannot say that it is a group. So this one is also not group, this one is also not group. Symmetric difference always form a group. You can take a multiple example and solve them, then this form is also symmetric group, also form a group, as well as abelian group also. Thank you so much for watching me, guy, and let's talk in the next chapter in next class with some other properties.